Today we start on important topics, completeness. We discuss first definition of completeness in previous class. Okay, completeness, every cauchy sequence in X convergent an element of S. Now we discuss one important theorem. Theorem says that R is complete. Okay, we do this problem. R be complete. One important theorem, and now prove this problem. Let Xn be a cauchy sequence in R. Be cauchy sequence in R. And delta greater than 0 be arbitrary. There exists a positive integer n in delta such that for all m greater than equal to n and n greater than equal to n, we have xn minus xn less than delta by 2. In particular, xn minus capital Xn less than delta by 2, or equivalently xn belongs to xn minus delta by 2, xn plus delta by 2 for all n greater than equal to. From this we made the following observation. Okay, first observation is for all n greater than equal to n, we have xn greater than xn minus delta by 2. And second observation is if xn greater than equal to x capital N delta by 2, then n belongs to 1 2 dot 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 n minus 1. Okay, thus the set of n such that xn greater than xn plus 2 is finite. Okay, that means this set is finite. Now we erase all this problem and we do further progress of that. Do further progress, that means thus the set of n such that xn greater than equal to xn plus delta by 2 is finite. Okay, now we're going to further, we shall apply these two observations below. we shall apply these two observations below. For delta equal to 1 and delta equal to x. Now let A such that x belongs to R. There exist infinitely many n. There exist infinitely many n such that x n greater than equal to x. Now we claim that S non-empty. S is non-empty, bounded above, and that supremum of S is the limit of the given sequence, and that supremum of S is the limit of the given sequence. Okay, now we're going to, from 1 we see that from 1 we see that x n minus 1 belongs to S. Hence S is non-empty. Okay. And from 2 it follows that x n plus 1 be an upper bound for S. Be an upper bound for S. Okay. Then we claim that y less than equal to x n plus 1 for all y belongs to S. Okay. Now if this are not true, then there exists a y. Then there exists a y belongs to S such that y greater than x n plus 1. Okay, and such that x n greater than equal to y for infinitely many. X n greater than equal to y for infinitely many n, and this implies that x n greater than x n plus 1 for infinitely many n. This contradicts to. Okay. Hence we conclude that xn plus 1, hence xn plus 1 be an upper bound for s. Okay. Next we erase all this problem. Now we're going to further discussion about this proof of this theorem RP complete. Okay. Erase this portion. Next, then by the LUV axiom, list upper bound axiom, there exists an L belongs to R, which is supremum of X, which is supremum of S. Now we claim that limit x equal to L. Let epsilon greater than 0 be given as L is an upper bound for S, as L is an upper bound for S, and xn minus epsilon by 2 belongs to S, as L is an upper bound for S and xn minus epsilon by 2 belongs to S. We infer that xn minus epsilon by 2 less than equal to L. Okay. Then, since L is the least upper bound for S, since L is the least upper bound for S, and xn plus epsilon by 2 is an upper bound for S, is an upper bound for S, we see that L less than equal to Sn plus epsilon by 2. Thus we have xn minus epsilon by 2 less than equal to L less than equal to xn plus epsilon by 2, or xn minus L less than epsilon by 2. Okay. So what we do, for n greater than equal to n, we have We have thus shown that limit n tending to infinity xn equal to L. Okay. Now we write this theorem. Rn becomes. Now observe that a sequence xk is cauchy in Rn. If and only if the coordinate sequence is cauchy in. Use the completeness of R. This one be complete. That means this one is Cauchy sequence in R, then this one is not complete, convergent in R. Okay, so obviously X K be convergent in R N. Okay, so next we discuss one problem. Let X be a complete matrix space. Questions. Let X be a complete matrix space. And assume that xn and yn are Cauchy sequences in X. Xn and yn are Cauchy sequences in X. We have to show that d of x in y in be convergent in R. Okay, now how we prove it? We know about that d of x in y n less than equal to d of x in x m plus d of x m y n, and this less than equal to d of x n d of x m plus d of x m x m and y m plus d of y m y n. This implies that d of x n y n minus d of x m y m less than equal to d of x n x m d of y m y. Okay, this implies that this one are cauchy sequence xn and yn. That means less than epsilon and epsilon for all n m greater than equal to a. Okay, then 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 obviously d of xn and yn less than equal to d of xm and ym. Okay, obviously this one are less than equal to this. That means this one is cauchy in R. Okay, t of x and yn is cauchy in R. Now this one is cauchy in R means this one is convergent in R. Okay, but if we do in this way, then this one is done. Then d of x and yn be cauchy in R, so convergent in R. Okay, any cauchy sequence is convergent in R, and otherwise if here in first we do, that means if x n cauchy in x and yn cauchy in x and complete x be a complete matrix space, that means if we do in this way, then obviously done. And otherwise another way we do it, that means x in cauchy sequence, so it is convergent in x because x complete matrix space, and y in cauchy sequence, so it convergent in y. That means dx in x less than epsilon and do y in y less than epsilon. Okay, for epsilon greater than 0. Then d of x in y n less than equal to d of x in x plus d of x y less than equal to d of x in x plus d of x y plus d of y. This implies that d of x and y n minus d of xy less than equal to d of x and x plus d of y and y. Okay, so x and converse, this means this one less than epsilon, this one less than epsilon equal to 2 epsilon for all n greater than equal to n, where n belongs. So d of x and y n converging to d of xy. Okay. Now we're going to another problem. Okay. This problem also tell us one important topic, d dz. We erase this portion first and then going further. So we write the matrix space, the problem, the matrix space C with the matrix DZW equal to mod of ZW is complete. So D of ZW equal to D of ZW equal to D of XY and D of UV. Now where W equal to U plus IV and Z equal to X plus IY. Okay, B2 complex number and D of XY and UV be the Euclidean distance in R square. Hence Zn tends to Z. if and only if the real and imaginary parts of shaded converges respectively to those of shade. Okay, hence hence we show that this matrix space be complete. Okay. Now we ace those problem. Okay. Next we're going to further discussion about further discussion about L1 norm 1 be complete. X and be cauchy in L1 and xi in V cauchy for all I. Okay. For each I. Let xi equal to limit n tending to infinity xi whole to the power n. Then we have to show that belongs to L1. Okay. We have to show that x equal to xi belongs to L1. Now then this one I equal to 1 to t less than equal to I equal to 1 to p. Then this tends to 0 since x I n be cauchy for each I. Okay, then this one is convergent, and obviously xi difference xi to the power a b tends to 0, and then this one is belongs to L1, so this one less than plus. Okay, hence hence xi whole to the power n tends to xi, and this implies that x to the power n tends to x belongs to L. Okay, so today we stop here. Then